Next part of redox. Next part of redox is about balancing the redox reactions. I'll do one, you'll do one. Okay. So while I'm doing, you will simultaneously do. Then I'll give you one more question so that you can do it on your own. Got it? Now let's see. Typically, when you have any redox reaction, if there are two if there are two different species which are undergoing oxidation and reduction, then that kind of a redox reactions are called intermolecular redox reactions. So here manganese is getting reduced from +7, it is changing to +2. So it is a reduction reaction. While iron is getting oxidized from +2 to +3. So you could notice that there are two different species which are participating in redox reaction. Got it? Then we call them as intermolecular redox reaction. Okay, this is an intermolecular redox. There are multiple ways of balancing it. Ion electron ion method is the most easier way and also the important way because it will give you a lot of insight over upcoming topics as well. Okay, so electron ion method is more or less like creating the ions first which are undergoing redox. So out of these, whichever the ions I'm writing are only the ones which are sensible for the reaction. For example, if you have K plus here, MnO4 minus plus Fe plus 2 plus SO4 2 minus, that is giving Mn2 plus plus SO4 2 minus plus Fe plus 3, right? That's it. Water and all is not necessary to write, all right, because that's not an ion. So this is what you would be writing first. Then you will delete those species which are just acting like spectators. They are not a part of redox, like K plus, SO4 2 minus, and SO4 2 minus here, right? So these are called the ones where you have this dash species. These are called spectator ions. Spectator ions. So remove that spectator ion. So what is left now? So we'll have MnO4 minus plus Fe plus 2 is giving Mn2 plus plus Fe plus 3. So this form which you write is called as ionic form. Ionic form. So this is like the first step that you need to do. Always write the ionic form. Okay. Once you have written the ionic form, try to separate two reactions here. The one which is undergoing oxidation or reduction on one side and the other one on the other side. So Fe plus 2 to Fe plus 3. And notice how many number of electrons are being transferred here. You can see there are 5 electrons being transferred here and there are 1 electron being transferred here. Okay. Now this reaction is a reduction, but it is only half reaction. That's why it is called reduction half reaction. This is called reduction half reaction. Henceforth, in the questions, if at all you see this abbreviation RHR, means you are talking about the half reaction which is undergoing reduction. The other one is oxidation half reaction. Oxidation half reaction. Electrochemistry will be using these terms a lot of time. So remember what is RHR, what is OHR. Okay. Clear, beta? Right. Now, see why we are talking about electrolysis or electrochemistry all of a sudden. See, in electrochemistry, what we do, we always deal with the redox reactions and we try to reduce and oxidize certain things in a procedure called electrolysis. This is a typical form of electrolysis. So in electrolysis, what do we have is we will have two electrodes here. There is one electrode on here and there is one more electrode here, correct? These electrodes, if at all you connect them to an external battery source like this, okay, and then try to make the redox reactions happening in this. Then the negative terminal where it is connected, that is called as cathode. So this is the cathode part, and the positive terminal where it is connected, that is called anode. Okay. Usually on the anode side, always you will notice oxidation takes place. On the cathode side, reduction takes place. Reduction reactions always happen on uh, uh, cathode side, and oxidation reactions happen on anode side. Okay, clear? If the setup is happening only in one cell, right, like this, with the help of an external battery, this is called electrolysis. This is called electrolysis, or the cell name is called electrolytic cell. Got it? So whatever I have written is an electrolytic cell. Clear, everybody? So here when I'm writing RHR, at RHR what will happen, beta? RHR always happen at anode. Sorry, RHR happens at cathode. Okay, it will happen at cathode. And at cathode, what is happening here? Reduction. So just keep that in mind. And at anode, always oxidation will take place. Now what you do, see, in any balanced reaction, in any redox reaction, the number of electrons given and taken should be same. And that's what we are trying to do. So to balance the number of electrons given and taken, I'll multiply this half reaction with 1 and this side of the half reaction with 5. And after doing that, add both of them. So now, after adding, you will get the second equation, which is called electron balanced, electron balanced redox, electron balanced redox. So what is the electron balanced redox? MnO4 minus plus 5 moles of Fe plus 2 is giving Mn2 plus 5 moles of Fe plus 3. This is the electron balance redox. Clear? Now, once you have electron balance redox, now you have to specify the medium of solution. Okay. So here it is an acidic medium. So for acidic medium, we will use simple logic that you will count the number of oxygens on both sides. Okay. So feed H plus ions on oxygen deficient side, oxygen deficient side, and feed, okay, half of H2O molecules. Got it? Sorry, my mistake. Oxygen rich side here, and half the molecules of water, half the molecules of water on oxygen deficient side. Okay, let me tell you how. Suppose, since this is an electron balanced reaction, now if you count the number of oxygens on left hand side and right hand side, here you will see there are here we'll see there are 4 oxygens. On the left side we have 4 oxygens, and on the right side we have 0 oxygens. So the difference in oxygen number is equal to 4. So on the deficient side, what do we add? We'll add 4 moles of water and double that with H plus ions. You have to double that with H plus ions. Now as you double it, what do we get? We will get this as MnO4 minus plus 5 Fe plus 2 plus 8 H plus is providing Mn2 plus 5 Fe plus 3 plus 4 H2O. Okay. Now this is called the redox you know, balanced redox reaction. Whatever we have done is a balanced redox reaction. Now to verify whether this redox reaction what we have done is balanced or not, or particularly correct or not. Now what do? You do charge balance. You do charge balance. Charge balance is figuring out how much is the charge on left hand side and on the right hand side. The charge must always be equal when you are writing an ionic form. See, left hand side, what are the charges I have? Here I have -1, here I have +10, and here I have +8. Okay. So that makes total how much beta? That will make total of 17, plus 17 charge. Here we have +2, here we have +15, and here we have 0. Again, it is coming +17 side. So that means the total charge has been balanced. If the charge has been balanced, that means the reaction that you have made is an redox balance reaction or balanced redox reaction. Okay. You are generally not asked about what are the spectators that you are using or balance the spectators. But by chance, let's say with the spectators, the information is given. Now bring back the spectators which were earlier given in the equation. So you can see it was KMnO4 plus 5 moles of FeSO4 plus. Now obviously on the product side, if you have to have sulfate, that means this acid must also be in sulfuric acid. So it must be 4H2SO4 so that it can give 8H plus, and that must be giving MnSO4 plus 5 moles of Fe SO4 thrice. But obviously here FeSO4 thrice will only be possible when Fe2 is there and 3 is there. Correct? It should be Fe2 and thrice. So if it is twice here, that means it should be 5 by 2. Correct? So that we can get exactly 5. Clear? And that plus how many how many potassiums we should have here, because potassium has to be balanced, it has to be K2SO4 as well. Got it? It has to be K2SO4 as well. So that's why now what you do, you multiply the entire equation again with 2, so that this here we are seeing K2SO4, so it has to be half as well. Correct? So that one potassium is balanced. So either you write it this way, or if you do not want to write without fraction, and that is what is expected in JEE mains or advanced, whenever it is been given, it is always asked within simple integer values. So now multiply everything with 2. So what is the final equation you will get? 2 KMnO4 plus 10 FeSO4 plus 8 H2SO4 is giving 2 MnSO4 plus 5 Fe2SO4 thrice plus K2SO4. Now look into it, everything is balanced. You can see 2 potassiums are balanced, 2 manganese are balanced. Check out sulfates, how many we have? 8 plus 10, total 18 sulfates. Here there are 2 sulfates, here there are 15 sulfates. So 17 plus 1, 18. So all the sulfates are also balanced. Here there are 8, how many we have? 8 to the 16, 16 hydrogens. That means here it should have been how many? 4 H2O should have been present. So here we should have 8 H2O. Okay. So you can see now the oxygen is also balanced. Here. So this is the balanced equation, including all the spectators. But like I said, that is not usually expected. But by chance, if this options are given like this, A, B, C, D, E, F, G, H, and you are supposed to find out what are the exact stoichiometric coefficients, then it will be useful. Is this part clear, everybody? Please check the rules. Check out what we need to do. Any doubt? Samyak, Shaurya, Ayushi, Pratisha, everybody?
Sir,
Utsa?
I had a doubt.
Yes, better.
Sir, it is like reduction half reaction, oxidation half reaction. Why is it known as half reaction?
See, redox is always a reaction where oxidation and reduction has to happen simultaneously. correct? There will not be have only reduction or only oxidation reaction, correct? So now
Yes.
that redox reaction you're separating into two reactions. You're showing like there is one half oxidation and there is one reduction, and then trying to balance both of them, isn't it? That's why
Yes, sir.
we're writing that whole reaction into two set of reactions where oxidation and reduction are represented separately. That's why it's called half reaction. Okay.
Okay, sir.
So,
Can
Yes, Vita.
so can you explain the last part again, like after
Sure.
adding the spectator atoms?
Sure. Whatever the question has been given, I'm using the same uh, spectators here. Okay. You can't add new spectators, obviously. The spectator which were used was potassium. Then there was sulfate on the right hand side. MnSO4 was given. So MnSO4 was kind of a hint that you must be using sulfuric acid here. Okay, it not necessarily has to be MnSO4. It could have been given MnCl2 also. Then you will use HCl acid. Hmm? So since it was given MnSO4, now I'm writing all of those. Like potassium is there. Obviously, if left hand side potassium is there, right hand side it should also appear. And how does potassium appear as a salt only? That is K2SO4. Okay. And after balancing of oxygen and hydrogen, now what we are trying to do, you're checking whether all these sulfates and everything is balanced or not. So for that, first in the given set of charge balance, whatever the values you got, you first use the same values. So 1, 5, 4. See, 1, 5, 8. You're using the same values. Here 4 means 8 only. 4 to the 8, correct? Again, I'm using 1 here, 5 here. But it looks like these are 5 Fe plus 3. But if I take Fe2SO4 thrice, that will become 10 Fe plus 3. That is wrong, right? That's why I have to take it as 5 by 2. Hmm. Similarly,
Okay,
when I
sir.
get K2SO4, I should get only one potassium because here it was only one potassium, correct? That's why I took it as half here. And 4H2SO4 is 4H2 is as usual carried, okay? And now I'm
Okay.
balancing everything again with multiplying that with 2, okay?
Yes, sir, got it.
Clear, everybody?
Sir, can you explain that adding spectator ions part again? Like,
Now
how did
listen.
you
What
implement
was the original question given? This is the original question given, okay? This is what has been given to us. Raw data. This is the raw data we have, okay? From here, what is the understanding, sure? That left hand side there is a potassium. Obviously, there should be right hand side, correct? And right hand side there is a sulfate. Obviously, the hydrogen, I mean the H2S, the H plus that must be coming with should be from some sulfuric acid. Okay. With that understanding, we are starting with the balancing. Okay. Correct. So what I did, I used that liberty that there could be some K2SO4 present on the right hand side. And same way the H plus must be coming from H2SO4. Correct. Putting these two factors and earlier whatever the balanced items, whatever we got, I'm putting all of them together now. Sure. Makes sense? Right. And once I keep all of them, in this equation, I'm trying to balance them properly. That there is one potassium, there has to be half of K2SO4 here. And there are 5 Fe here, so there has to be a 5 Fe. That's why I made it as 5 by 2. Okay. And just not to keep it in fractions, I'm multiplying everything with nearest integer. Okay. Let us keep doing multiple questions, then you'll get more clarity on that. Check it out. Now, here is the interesting part. On the right hand side, he hasn't giving enough hint to understand whether it is HCl or H2SO4 or HNO3 or anything. You could take anything. That's why I said this is never compulsory, sure. You will never be asked like whether what is the uh, balanced equation with the spectators, because we are not sure whether this H plus is actually being derived from HCl or HNO3 or H2SO4 or HClO4. We don't know. whatever the acid that is being used. Okay. Since we are not sure of, you will not be usually asked with this. You have to end up where, at this fourth step, that is the redox balance reaction. Correct? So let us try to get this same fourth step for this reaction also. The minute you see, what do we do? First, we check out whether it is, what is the type of reaction here? Check what is happening. Chromium here, two chromiums, because you need to always check out for two chromiums, everybody. We shouldn't check out for one chromium. Why? Because redox reaction is always with respect to a molecule, not with respect to an individual. So therefore, here it is one molecule. One molecule contains two chromiums. So for two chromiums, what is the charge? Plus 12. And since there are two chromiums on the left hand side, make sure that there are two chromiums on the right hand side. Whether it is given or not, you should always mention that. So for two chromiums, how much is the total charge? Plus 6. Similarly, if at all I have two carbons here, how much is the charge? Plus 6. So that makes two carbons on the right hand side. That makes it plus 8. Now, this is giving us the evidence that plus 12 to plus 6 is a reduction, while plus 6 to plus 8 is an oxidation. This is an oxidation reaction. Okay. So on one end we are getting reduction, the other end we are getting oxidation. Clear? And now you have to write the half reactions. So what do we do? First we have to write the ionic form. So ionic form is Cr2O72 minus. I'm removing the spectators. C2O42 minus. That is giving Cr plus 3 plus, 2Cr plus 3 plus 2CO2. That's it. H plus and water, you don't have to worry about it. We will be adding it anyway at the end. Now write the RHR and OHR. What is the RHR? RHR is Cr2O72 minus. That is giving 2Cr plus 3. OHR is oxalate. Or this is oxalate ion, by the way, in case if you do not remember the name. This is dichromate. So the oxalate ion is converting into 2 moles of carbon dioxide. How many electrons we have seen here? 6 electrons got transferred here, and 2 electrons got transferred here. Okay. Now to balance this, I have to multiply RHR with 1 and OHR with 3, and then add them both. So after adding, we will get second one, which is about electron balance redox. Electron balance redox. And that is Cr2O72 minus plus C2O42 minus plus. Okay. Sorry, that's it. That is giving 2 moles of Cr plus 3 plus, not 2, yeah, 2 moles plus 6 moles of CO2. And how many oxalate? 3 moles of oxalate. Okay. So this is the balanced equation.
So can you explain again why we have to multiply by 1 and 3? I didn't understand.
How many electrons oxalate is consuming? Reduction is consuming electrons, 6 electrons. अगर ये 6 electrons consume कर रहा है तो देने वाला भी 6 देना चाहिए ना बेटा. But as per the equation, it appears like it is giving only 2.
अच्छा, that way. ठीक है.
So now, once you get this, you will have the electron balance redox. You got the electron balance redox. Now you read the solvent. Okay, it is acidic medium. So what is that we learned in acidic medium? Always add water on the deficient side and H plus on the rich side. So I'll put that. Count the number of oxygens. 4 3 is 12. 12 plus 7, 19. So there are 19 oxygens on total on the left hand side. And how many oxygens on the right hand side, 12 oxygens on the right hand side. So what do we need to add? We have to add differential part of it, which is 7H2O on the right hand side, and counterbalance that with 14H plus on the left hand side. And now the fourth step is about, balanced redox reaction. Balanced redox. So what do I get? Cr2O7 2 minus plus 3 moles of C2O4 2 minus plus 14 moles of H plus. That must be giving 2 moles of Cr plus 3 plus 6 moles of CO2 plus 7 moles of H2O. So this is the balanced equation. And lastly, to just check it out whether we are done correct, what do we do? Charge balance. Check out what is the total charge on the left hand side, on the right hand side. This is -2, -6, plus 14, plus 6, 0, 0. So here you can see we are getting +6 on the left hand side, +6 on the right hand side. So this is perfectly balanced. So please check. Let's check out how to work out in the basic medium. See, as long as medium is concerned, the medium's role only comes at that third step. Up to the balancing, regular balancing, nothing, everything is same. Okay, so we'll do the balancing as usual. So now, since we got the rhythm of it, let us do even more quickly. Okay, this time we'll write the ionic form even more easily and continue it quickly here. Ionic form. So MnO4 minus plus I minus is giving MnO2 plus IO3 minus. Okay, I'm writing RHR because now I don't have to prove again and again that it is a redox. So just by watching them, you should be able to figure out that MnO4 is actually getting reduced. OHR, where I minus is getting oxidized to IO3 minus. Here the oxidation is changing from +7 to +2, making 5 electron difference. Here it is -1 to +5, okay, making 6 electrons difference. So to ensure number of electrons given and number of electrons taken are same, you will cross multiply them, okay, to the nearest value. So this is what you will do. Correct? Sorry, this is MnO2, my mistake. MnO2 is +4. Okay, MnO2 is +4. +4 means 3 electrons. 3 electrons difference is what you will notice. Correct? So what is the cross multiplication that we will apply now? Here we'll multiply 2 and here it will multiply 1. And now you add the equations here. So you'll make this as 2 MnO4 minus plus I minus is giving 2 MnO2 plus IO3 minus. This is what you will have. Okay. Now is the rule for medium. Okay. Rule for basic medium. In the case of basic medium, what you will do, okay, add H2O on the rich differential side of oxygen. And counterbalance with double the number of OH minus. So it's kind of opposite to what we have done it for acidic medium. So I'm taking that. So let me show you left hand side and right hand side how many we have. 8 oxygens on the left hand side 7 oxygens on the right hand side. Okay. So where is the rich side? Rich side is here. So on the rich side, you will be adding water. So how much is the differential water? 1. And on the deficient side, you will be adding double the number of OH minus. Okay. So that would give us equation as 2MnO4 minus, correct, plus I minus plus H2O. That must be giving 2MnO2 plus IO3 minus plus 2 moles of OH minus. Check out the charge here now. -2, -1. Total charge is -3. 0, -1, -2. Total charge is -3. So that means whatever you have attempted is correct. Please check this out, everybody. Let me tell you again. See, the balancing of basic medium and aqueous solution, both would be same. You will always add the water molecules to the rich side of the oxygen and counterbalance that with double the number of OH minus. Okay. On that note, I want you to do the next one, everybody. Check it out. MnO4 2 minus is giving NaMnO4 and MnO2. Got it? Let's do it together, everybody. First, write the ionic form. Ionic form looks very simple, for these kind of reactions, but going ahead, if you have any multiple complex reactions, it always helps. So it's suggested always write the ionic form. Okay. Next, write the RHR and OHR. See, reduction. See, what's happening is MnO4 2 minus is getting reduced to MnO2. Check out the oxidation state from +6 to +4 it is happening. So 2 electrons is what it is consuming. So OHR, if you notice, because you have only one reactant here, 2 minus, so that itself must be involving into uh, reaction as well here. So what do we have? MnO4 2 minus. Here it is at +6 converting into +7. So 1 electron is been transferred here. So same MnO4 2 minus is involved in oxidation also as well as reduction also. And now to balance it, I need to multiply this with 1. And to balance it, you have to multiply this with 2. Okay. Clear? I'll give you 2 minutes to finish the rest of the part. Okay. Do that quickly. Check the charge balance also, everybody. If you check the charge balance, how much you are getting? -6 on the left hand side and -6 on the right hand side. Clear? Right. Do the next quiz. Now you should be a little faster. Okay. Let's keep on doing faster now. Everyone, come on. So I'm just writing the basic framework, what we have to write, basic steps. Okay. So you can keep following that. I would suggest you keep doing on your own. Don't see it much on the board. Okay. I'll just keep doing. I'll just keep writing here and put. Please do check, everybody, if you are able to reach to this point. In this case, OHR is peroxide converting into O2. It's transferring 2 electrons. ClO2 is converting into ClO2 minus, which is transferring 1 electron. And cross multiplying them, making their electrons balance. This is what I have got. Please check if you have got the same thing. Okay. So what it is the learning that the number of oxygens on either side is same already. Correct. So now it is not about, based on acidic medium, based on deficiency of oxygen. So in that case, the hint that you need to notice is this: in the given reaction type, the raw data which has been given, where is the OH minus and H2O? Accordingly, you will write down in the product. Correct? So now, obviously, between these two, I have to balance. So here it should be double, here it should be one time. Correct? Then only it will be balanced. And obviously, the hydrogens which you are putting it as double is already getting balanced by this water molecule. Correct? So that's why. What do I put? Suppose if at all I put 2 moles of OH minus and 1 mole of H2O. Okay, check whether it is going to get balanced or not. So I will have this as H2O2 plus 2 moles of ClO2 plus 2 moles of OH minus. That is going to give us 2 moles of Cl2 minus plus O2 plus H2O plus O2 plus H2O. Okay. Check if it is balanced or not. If it is balanced, that means you're done. Whatever you're done is correct. Otherwise, if it is charge is not balanced, you keep doing permutations here. Once you do with 2 moles of OH minus, once you do with 4 moles of OH minus, once you do with 6 moles of OH minus. I hope you're getting my point. Yeah. So when you keep doing that balancing, then accordingly you can check out whether the charge is balanced or not. Because on the right hand side there are two -2 charge, I would actually require -2 charge on the left hand side. That's why 2 OH minus itself is going to balance it. Clear, everybody? This case is understood? Right. Let me go back to this case here. Have you noticed something about this case, the earlier case, MnO4 2 minus giving MnO4 minus and MnO2? If the same species, remember everybody, if the same species is being involved into redox reaction, where it is undergoing reduction and the same molecule is undergoing oxidation. Not just molecule. If you notice carefully, within the molecule, there are two different types of atoms. One is manganese, one is oxygen. Is oxygen involved here? No. Who's involved? Only manganese atom, isn't it? Now remember, within the molecule, if only one element is responsible for both oxidation and reduction, okay, then this is called as disproportionation reaction. Disproportionation redox reaction. Okay, let me remind you again. If single elemental species is responsible for both oxidation and reduction, then the reaction type is called disproportionation redox reaction. Okay. Coming back to our question which we just solved, this is a normal intermolecular redox. Intermolecular redox. Because there are two different species involved. You know, both of them are going oxidation and reduction. Okay. Clear on that?
सर
Yes, beta.
सर वो H2O नहीं होगा?
हाँ, 2H2O, sorry. 2H2O. Okay. Why? Why is there 2H2O here? Reason being, left hand side already you have two hydrogens here. Okay. That need to be balanced. Clear? Done? See the next one. Cl2 in the presence of basic medium is giving KOCl, KCl and H2O. So first let me write the ionic form of it. Okay. The ionic form essential for redox balancing. Cl2 is giving OCl minus plus Cl minus. Okay. OHR, oxidation half reaction, is Cl2 is converting into OCl minus. RHR is making Cl2 to convert into 2Cl minus. Here it is going from 0 because there are two chlorines. Make sure there are two on the right hand side also. Here it is plus 2 because each chlorine is plus 1. So two chlorines make it plus 2. Here it is 0 and two chlorines make it minus 2. So number of electrons transferred are 2 here. Number of electrons transferred are 2 here. So both of them are already electron balanced. Both of them are electron balanced. So that means we will have 2 moles of Cl2 converting that into 2 moles of OCl minus plus 2 moles of Cl minus. Okay. Or in short, I can actually remove that 2. It is not essential. Okay. Clear? If the common term is coming, you can always remove that. Correct? So now it is balanced already. Check out the number of oxygens. If you notice the number of oxygens, right hand side there is 1 oxygen. Left hand side there are 0 oxygens. So the rich side is here. On the rich side, I'll be adding water molecules. So you will have this as plus H2O. And on the right hand side, we'll have the double the number of OH minus. So that implies the final reaction is Cl2 plus 2OH minus is giving OCl minus plus Cl minus plus H2O. And here also single atomic species or single element is giving oxidation and reduction. So this is disproportionation reaction. So this is also disproportionation redox reaction. Okay. That's right, Utsa. Clear, everybody? Now, I'm already writing case by case. I'll just summarize the cases again. Notice this, everybody. Okay. Types of redox. Types of redox. The first one is intermolecular. Intermolecular redox. If you notice the example, something like MnO4 minus plus I2 is converting into, sorry, I minus is converting into I2 plus Mn2 plus in acidic medium. So this is intermolecular. Next, intramolecular. Intramolecular means you have, one molecule in which there are two different species. For example, I have Cu2s. And Cu2s, let's say, in acidic medium, it is converting into 2 moles of Cu2 plus and sulfur is converting into SO4 2 minus. SO4 2 minus. Okay. So molecule is only one, but within that there are two distinct atoms. One of them is undergoing oxidation, the other one is undergoing reduction. Then you call it as intramolecular. Intramolecular are more famous for balancing their charges and not the solvents, because decision of solvent is very difficult in intramolecular. That's why you will not be asked a question to balance the intramolecular. You will be always asked the challenge of balancing their electrons. Okay. For example, if you have FeS2, FeS2, in dilute OH minus here also it will convert into Fe plus 3 and sulfur will become SO4 2 minus. Correct? sorry, 1 sulfur, FeS2 is converting into Fe plus 3. Now notice FeS2 is converting into Fe plus 3 and 2 moles of SO4 2 minus. Now you need to understand one thing here. Iron is undergoing oxidation because it is going from plus 2 to plus 3. Sulfur is also undergoing oxidation. So where it is minus 2 on 2 sulfurs and plus 12 on, 2 sulfurs. So here also it is oxidation. So you must notice that oxidation is happening here also, oxidation is happening here also. So is it a complete reaction? No, it is a half reaction. But yet we call it as intramolecular half reaction. Intramolecular, okay, half reaction. This is about intramolecular. And lastly, sorry, one more, disproportionation. Disproportionation redox. Like we just learned, Cl2 is converting into ClO minus and Cl minus. This is one example. P4, phosphorus in the presence of base, will convert itself into PH3 plus HPO2 minus, right? Sorry, H2PO2 minus. Got it? I2 in the presence of OH minus concentrated will convert into I minus plus IO3 minus. That is also disproportionation. So these kind of reactions where only one atomic species is involved or one elemental atom is involved, which is responsible for both reduction and oxidation, that is called disproportionation. And lastly, comproportionation. Comproportionation redox. It is just the reverse of disproportionation. That's it. So you're combining two groups to form a molecule. Okay. So like if at all I have Br minus and BrO3 minus. Okay. In acidic medium, the reverse will happen. It will convert into Br2. Okay. So basically, Br2 is the one which we are talking about, which is undergoing reduction here, which is undergoing oxidation here. But it is in a reverse way. So the same disproportionation in the reverse order is called as comproportionation redox. Okay. So please do check the terminologies. So there are mainly 4 types of redox: inter, intra, disproportionation, and comproportionation. Okay. Okay. So in the cases of redox, first we'll start with the intramolecular. If two different atoms are undergoing oxidation and reduction, then we call it as intramolecular. So notice in copper 2 plus here, copper 2, this is at plus 1 oxidation state, each copper, and here it is undergoing plus 2 oxidation state, while sulfur here is minus 2 converting into plus 6 oxidation state. Correct? Plus 6 oxidation state. This is what is happening. Okay. So notice how many electrons are transferred from one species to the other here. So there are two coppers, there are two copper here. So into 2. So total charge is plus 2 for 2 coppers. And similarly, if I take 2 coppers here, total charge is plus 4. So from plus 2 to plus 4, how many electrons are transferred here? 2 electrons are being transferred. Similarly, from minus 2, it is changing to plus 6. So how many electrons are transferred totally? 8 electrons have been transferred. Have you noticed that this is oxidation as well as this is oxidation as well? So the total number of electrons are oxidation electrons only. So I can say total oxidation electrons are 10. total oxidation electrons are 10. Okay. In fact, if you want to find out what is the valency factor for this one, okay, if you remember, we came across a definition about, what is a valency factor already, isn't it? We learned that number of equivalents is equal to number of moles into valency factor or N factor. Okay. And when it comes to redox reaction, everybody, whether it is oxidation or reduction, any species that is involved in oxidation, you notice the number of electrons that is involved. Now, as a molecule, Cu2s, overall it is involving 10 electrons. That means it is giving away 10 electrons. So the valency factor automatically becomes 10 in this case. So valency factor is 10. Hence, if I have to write the number of electrons here, so what would I write? I will write this as number of equivalents divided by 10. Correct? This will be number of equivalents divided by 10. Correct?
So can you
And that's what
explain
I'm
this
writing.
equivalent part again, valency factor?
See, we discussed about what is a valency factor, in various type of reactions as well. In fact, if you have an acid, we discussed that the number of H plus ions an acid can give, that will be its valency factor. If it is a base, how many OH minus it can give. If it is a salt, what positive charge or negative charge, it is total charge which it is carrying. Okay. But all of these valency factor definitions are valid for non-redox. When it comes to redox reaction, you only need to check the species for which you are finding out equivalence, how many electrons that species is involving in that reaction. That becomes a valency factor. Okay. Now, in this case, if you notice Cu2s, the overall number of electrons which is involving, and because Cu2s is only getting oxidation here, how many electrons are involved in that? 10 electrons in total. So that 10 electrons will become the valency factor here. Okay. Clear, beta? And what is the
Yes.
definition of equivalence? Equivalence is equal to number of moles into valency factor or Z factor. So N is equal to equivalence by valency factor. Okay. So what will be the number of moles here? X by 10. X by 10 is the number of moles here. Okay. Clear? X by 10 is number of moles here. Now notice, if this is X by 10, how many moles of copper 2 plus we are, getting based on the balanced equation here? Based on that, I can say, if X by 10 is the number of moles which are present for copper 2 plus, how many moles of copper 2 plus should be formed here? It should be 2 times of that. How many sulfate should be formed here? It should be same as X by 10 times. So these are number of moles, correct? And remember, number of moles multiplied by valency factor will give you equivalents back. So multiply that with 10, multiply that with number of electrons involved by copper 2 plus. So one copper 2 plus is involving how many electrons? Now we are not talking about Cu2s. I am talking only about Cu2 plus. Cu2 plus is coming from Cu plus. For 1 mole, 1 electron is transferred. So that becomes its valency factor. And for sulfate, for 1 sulfate, from where it is coming from? From this sulfur. So how many electrons were transferred? 8. So into 8. So 2x by 10, 8x by 10. These are the number of electrons that are being involved here. Sorry, number of equivalents that are being involved here. Okay. Clear, everybody? Have you noticed something? How many equivalents Cu2 plus has now? Cu2 plus, if you notice that it is simply sum of these two. Yes or no? Now, this is very interesting fact. This will only happen with disproportionation reaction. Only with, okay, sorry, intramolecular. Only with intramolecular and disproportionation reaction. Because in disproportionation also only one atom or one molecule is involved. Okay. So whatever be the number of equivalents of Cu2s, that has to be same as the number of equivalents of this one plus this one. That's why if you add these two, you'll again get X only. So this is a proof to explain that number of equivalents of the reactants will be equal to sum of the number of equivalents of the products. Got it? In which case, in disproportionation or intramolecular. Now notice this. As2S3 is giving 2As plus SO2. So each sulfur is at -2 oxidation state and arsenic will be made into +6 oxidation state for two arsenic. And for 2 arsenic here it will be 0. And for 3 sulfates, each sulfate will have +4. So total it will be +12. So from -2 to +12, total 14 electrons. +6 to 0, 6 electrons transferred. These are the number of electrons which have been transferred. Okay. Now notice how many electrons are being present here. +6 to 0 is actually reduction. -2 to +12 is oxidation. Now, net electrons involved by As to S3 will be equal to how much? 14 minus 6, the mod of it. So how many electrons? 8 electrons. So 8 electrons is the net number of electrons that have been involved here. Correct? Sorry, I made a mistake. For 3 sulfurs, it is -6 beta. So that makes it +18. So +18, 18 minus 6. So how many? 12 electrons. So net number of electrons are 12 electrons. Okay. So by chance, if I ask you, what is the equivalent weight of As2S3? So simply check out its molecular weight and divide it by total number of net electrons transferred. In this case, it is 12. Got it? 12 will be the valency factor. Okay. Clear? Now, if this is 12, how much will be for arsenic? See, arsenic has transferred how many electrons? For 2 arsenic, 6 electrons are transferred. For 1 arsenic, how many electrons will be transferred? 3 electrons. So equivalent weight of arsenic will be equal to molecular weight of arsenic divided by 3. Similarly, what will be the equivalent weight of SO2? Equivalent weight of SO2. That is equal to molecular weight of SO2 divided by number of electrons transferred here. So how many? For 1 sulfur, it is coming from 1 minus 2 here. So which means 6 electrons. So 6 electrons have been transferred. Correct. So if by chance if you were asked what is the equivalent weight, this is what you will do. These 12 are practice ones. You're supposed to practice, figure out what is the valency factor in all of them. Okay. For the reactant, see these many number of disproportionation as well as intramolecular reactions I have given you. So please do practice what is the valency factor in each case. For now, you will do one important one. This is a very, very important one. Asked many times in JEE, right? So let's see how we can calculate the valency factor of FeSCN thrice. Ferric thiocyanide. Okay. Clear? So always write the half of reactions and check how many electrons are being transferred in all the cases. So starting with iron. Okay. So what I will do, I will take Fe plus 3 because SCN together is always going to carry -1 charge. So Fe plus 3, it is converting into Fe plus 2. which means it is a reduction reaction. Number of electrons transferred are 1. And see, first I can explain you a structure. Sulfur connected to carbon connected to nitrogen. This is how the structure would be, with sulfur having negative charge. Okay. So it is like sulfur and nitrogen. All of them are pulling electrons from carbon with 4 bonds, because it is pulling with pulling electrons with carbon. Carbon will attain +4 charge. And now sulfur already has -1 charge, and it has pulled 1 electron towards itself. So that makes it -2. While nitrogen, it has -3 charge together. Correct? Why? Because it is pulling electrons all the way from carbon. So -3. Okay. So these are their oxidation states. So I can see there are 3 sulfurs. This is the usual mistake. Check out how many compounds are given. 3 sulfurs. Each sulfur is carrying -2, and that is converting into SO4 2 minus. Similarly, 3 carbons are involved. Each carbon is carrying +4 charge, and that is converting into CO3 2 minus. And number of electrons given taken should be same. So 3 here and 3 here. And lastly, nitrogen. 3 moles of nitrogen with 3 minus charge. Okay. So that would convert this into 3 moles of NO3 minus. Okay. Now look into how many electrons have been transferred in all the cases. -2, here total it is -6. Correct? Here one sulfur is +6. So total it is +18. Similarly, here it is +12, and each carbon has +3. So +3, sorry, +4. Each carbon has +4. So how many electrons are transferred? Again, +12. So there is no electron transferred in this case. Next, nitrogen, -9, changing into +5. So one nitrogen is +5. So this will become +15. 3 of them will become +15. Okay. So have you noticed carbon is not involved into oxidation or reduction? But sulfur is definitely involved. How many electrons? 24 electrons. Correct. And -9 to 15, this is also 24 electrons. Correct. So notice total number of oxidation electrons. How many we have? 48. Next, total number of reduction electrons. Total number of reduction electrons, 1 electron. Okay. Which is this one? This is the only one which is undergoing reduction. So what is the net number of electrons? Net number of electrons transferred. That will be equal to 47. Therefore, equivalent weight of Fe SN thrice. Okay. So that would be equal to molecular weight of Fe SCN thrice, that divided by 47. Please do check. Any doubt? See, iron here is actually +2. From there it is changing to +3. So which makes it 1 electron transfer. Carbon here, when it is Cn minus, it is at +2. And there are 6 of them. So it has to convert into 6 moles of CO2. Then nitrogen. There are 6 of nitrogen, each with -3, changing to 6 moles of NO3 minus. And here total charge is 12. Here each carbon is 4. So 6 fours 24. And here it is minus 18. And each one has plus 5. So 30 plus 30. Okay. So number of electrons which are consumed here is 1 electron. And here it will be 2 electrons. And what about here? So minus 18 to 0, it will be 18. So 0 to 30. So total it will be 48. So 48 electrons. So this is the total number of electrons transferred. Notice this is reduction. This is oxidation. This is oxidation. So net result is net electrons transferred will be equal to 12 plus is this is 60. Okay, clear? And here, sorry, this is not reduction. This is also oxidation. My mistake. It is also oxidation. So net is 60 plus 1. So how much it is? 61. Clear? So if I ask you what is the equivalent weight of K4FeCN6, okay, K4FeCN6. So you will simply write this as molecular weight by 61. Next time. Next, equivalent weight of uh, Fe plus 3. Okay, Fe plus 3 is coming from Fe plus 2. So it will be molecular weight by 1. Equivalent weight of carbon dioxide. That would be equal to molecular weight by how many for one carbon you need to check. For one carbon of carbon dioxide, we have plus 4 coming from plus 2. So 2 electrons. Next, equivalent weight of where is it? HNO3. Alright, so that will be equal to again molecular weight by, for one nitrogen, how many electrons we are transferring here? Here it is plus 5 and here it is minus 3. Correct? So 8. So 8 electrons have been transferred. Please check. Any doubt? Okay. So if it comes to intramolecular, how to calculate, I think that is easy to understand now. Suppose if it is intermolecular, it is even more easier. All you need to check out is number of electrons transferred. That's it. So from here, manganese here to here, 5 electrons are transferred. Iron here to here, there are 1 electron transfer. So that's what you have to figure out. Equivalent weight is equal to m by z. Z is a valency factor. So m by 5 for this one and m by 1 for this one. This is about simple intermolecular redox reaction. Okay. Now see the difficulty. What if you have cases where I need to find out the equivalent weight of every other species? Okay. Within the reaction, all the reactants and all the products. But there are certain reactants which are participating in the reaction, but they are not redox reactions. Like HCl. When it comes to HCl, if you notice, it is appearing like as if it is involved in redox reaction because it is converting into Cl2. But the question mark is, are all the hydrogens which are, are all the chlorines which are present here on the reactant side, are they all converting into Cl2? Answer is no. And that's what we'll try to figure out. Question is, calculate the equivalent weight of K2Cr2O7 as well as equivalent weight of HCl. Okay. See, don't think like, sir, HCl acid equivalent weight is molar mass by 1 because valency factor is 1. That is purely for non-redox. Only acid-base reaction ho raha hai. HCl plus NaOH is giving NaCl plus H2O. These kind of acid-base reactions are happening. Only in such cases, you will think them as an acid and check out how many H plus they are giving. Here it is not the case. Here it is a part of redox. So first, let me show you how to figure out the half reactions and overall reaction. See, One thing I know that Cr2O7 2 minus, okay, is converting into 2 moles of Cr plus 3. Okay, because I can remove this chloride separately. So from plus 12 it is changing to plus 6. So 6 electrons have been transferred. Okay, overall 6 electrons have been transferred. From which part? HCl. If you notice the HCl here, some amount of Cl minus. So I'll write down that HCl is converting into Cl2. So to make it balanced form, I can put 2 here. So that means from minus 2 chlorides, it is converting into 0. So 2 electrons are being transferred in this case. Okay. So 2 electrons have been transferred. So if at all I have to counterbalance, what will I do? I will have to multiply this with 1 and I will have to multiply this with 3. Now add them. What do I get? I will get this as Cr2O7 2 minus plus 6 moles of HCl is giving 2 moles of Cr plus 3 plus 3 moles of Cl2. Okay. But now notice problem what happens is it appears like there are 6 chlorides and 6 here. But in the options it is not like that. There are chlorides here also. There are chloride here also. Correct. And there is water also that which I need to balance. So first let us try to balance oxygen. That is a better way which we know. So balancing oxygen, if you notice, balancing oxygen, you will find there are 7 oxygens on the left hand side and 0 oxygens on the right hand side. So difference in the oxygen value is 7. So which means I need to add 7 H2O here and double the number of H plus ions. And then add them. What do I get? I'll get this as Cr2O7 2 minus plus, now tell me, where would I get this 16H plus? ध्यान से देखना. See, 7 water molecules are being balanced, but to balance this 14 H plus ions, already it appears like there are 6 HCl. Already there are 6 HCl. That means 6 H plus ions are balanced. So how many extra I need to balance here? 8. Correct. So that means 6 HCl was originally balanced. Now I have to add another 8 HCl. And this will convert into 2 moles of Cr plus 3 plus 3 moles of Cl2 plus 7 moles of H2O. Got it? Now listen up. This HCl was a part of redox, but this amount of HCl is a part of solvent. It is acting like a solvent, a medium. And of course, without this also we cannot make a reaction, which means if I write the overall reaction here, so this is what happens. Cr2O7 2 minus plus 14 HCl, that is converting into 2 moles of Cr plus 3 plus 3 moles of Cl2 plus 7 moles of H2. Okay. Now we know that total number of electrons transferred are how many here? You can see there are 6 electrons here. If I multiply that with 3, I mean, we got it already that this is the equation which we got. So the number of electrons transferred or given or taken are 6. Same way, if you have to do it for this one, how many electrons have been transferred? Check out. The same 6 electrons are now transferred not by 6 HCl. It is transferred by 14 HCl. So hence, equivalent weight in this case will be molecular weight by 6. Here it will be molecular weight by, now listen up everybody, for 14 HCl in this reaction 6 electrons have been transferred. So tell me for 1 HCl how many electrons will be transferred? 6 by 14 electrons. So I can say that this is molecular weight by 6 by 14 electrons have been transferred. Hence equivalent weight of HCl in this case will be equal to, this will go 3 times and 7 times. So 7 molecular weight by 3. Okay. So this would become the equivalent weight of HCl. Please do check. If the valency factor is asked, it will be 6 by 14 or 3 by 7. Right. Let me discuss. See here, zinc stands at 0 oxidation state. Zinc stands at +2 oxidation state. So there should be 2 electrons transferred. While nitrogen here stands at +5 oxidation state, while nitrogen here stands at -3, because here it is NH4NO3 is basically NH4 plus and NO3 minus. So the only compound, only position where the nitrogen is changing is in the ammonium form. So from here to here, how many electrons it is changing? 8 electrons. So from here to here, how many electrons are changing? 2 electrons. So if I have to counterbalance, then I must have 4 zinc. So I'm writing directly 4 zinc should be present to convert that into 4 Zn plus 2. Okay. And here in the case of HNO3, it is converting into NH4 plus. So there is 8 of electrons. So only one should be present here. Okay. So by adding, I should get this as 4 Zn plus HNO3. Right. That must be giving 4 Zn. Now let me bring back NO3 again twice plus NH4 plus NO3. Okay, NH4 plus and NO3. NO3 minus. Okay, clear? Now if you notice it here, one thing first, take out nitrate groups. How many nitrate groups we have? Check out. We have 4 to the 8 plus 1 9 and one more nitrogen is changing. So total 10 nitrogen groups should be present. Here it appears like only one is there. So how many extra nitrogens I should have? At least 9, right? So that means at least I should have 9 more HNO3 to make sure everything is converting into this product form. Okay, everything is converting into this product form. And now, if it is 9, that means total number of hydrogens. I'm doing a counter way, okay? Not balancing oxygen, but checking a counter way here. 9 plus 1, 10. 10 hydrogens are present, out of which 4 hydrogens are already lost here. So there should be 6 hydrogens. So that accounts for 3 H2O. That accounts for 3 H2O. Okay. So now let me add all of them. So what do I get? 4 Zn plus 10 HNO3. That is giving 4 ZnNO3 twice plus NH4NO3 plus 3 moles of H2O. Okay. Now if I have to find out the equivalent weight, it will be molecular mass by 2, because zinc is only releasing 2 electrons. But what about this one? You see, total from this HNO3, how many electrons we have to push? 8 electrons we have to push. But I have how many molecules? 10 molecules. 10 HNO3 are pushing 8 electrons. So 1 HNO3 will push how many electrons? 8 by 10. So therefore, here equivalent weight will be equal to uh, molecular weight by 8 by 10. Okay. So therefore, valency factor of HNO3 is equal to 8 by 10. Please check, everyone. when there is a disproportionation reaction, how do we find out the equivalent weights? Okay. Again, here there are multiple methods. I'll show both the methods here. How to calculate the equivalent weight in disproportionation reaction. See, first of its kind is figure out how much is the oxidation type and how much is the reduction type. From here to here, you know that chlorine, it is getting reduction, and this chlorine going to OCl, this is getting oxidation. Same logic will apply here as well. If the same atom undergoes oxidation reduction, it is called disproportionation reaction. Now you see I2 is converting into I minus as well as IO3 minus. So which means this is also a disproportionation reaction. Now what I'll do, first I'll write the RHR and uh, OHR as usual. So I2 will first convert into 2 moles of I minus. This is RHR. OHR will be equal to I2 converting into 2 moles of IO3 minus. So the number of electrons transferred in this case are 2 electrons. Number of electrons transferred here are 10 electrons, because here it is 0, here it is plus 5 for one iodine. For two iodines, it will become plus 10. Here also for two iodines, it is 0. So 10 electron. So how do we counterbalance this part? So multiply this with 5 and multiply this with 1 and then add them both. So now overall reaction we will have here is 5 plus 1, 6. So 6 moles of I2 is converting into 10 moles of I minus plus 2 moles of IO3 minus. Okay. Now while we are doing, how many electrons were transferred in total? 10 electrons, correct? 10 electrons got involved in oxidation and reduction, correct? So when the number of electrons which are involved, right, that becomes the valency factor for a compound. Got it? So you know that valency factor is always measured for 1 mole. So you can see 6 moles of iodine is responsible for 10 electron transfer, which means 1 mole of iodine is responsible for how many electron transfer? 10 by 6. Okay. So therefore, equivalent weight will be equal to molecular weight by 10 by 6. Okay. This is 10 by 6. Now notice, another method is that you know that RHR and OHR. Okay. And earlier we already proved one thing, that for disproportionation as well as for intramolecular, we can actually add the individual equivalent weights, individual equivalents. We can add that. So same thing I'm doing it here. Equivalent weight in RHR. Equivalent weight in RHR will be equal to molecular weight of I2 divided by 2 electrons. Similarly, equivalent weight of OHR. Equivalent weight of OHR, that is equal to molecular weight of I2 that divided by 10 electrons. So therefore, now I can say equivalent weight of I2 in the reaction will be equal to molecular weight by 2 plus molecular weight by 10. Okay. So then what do we get? We will get this as 6 molecular weight by 10, or simply this is equal to molecular weight by 10 by 6. So you can notice that either you use it in this method, or you can directly, since you know the number of electrons transferred, you can directly use this method. In either of the cases, you should know how to calculate equivalent weight of the reactant. Okay. So please do check. So if you have to balance this reaction, what you can do, because we already know how many electrons are being given here and how many electrons are being transferred here. This is the electron balance reaction already. So 6I2 is giving 10 I minus plus 2 IO3 minus. So which makes it total of 6 oxygens here, right? This is the rich side. On the rich side, what do we do? So to balance that, I have to add 6 moles of H2O and counterbalance that with double the number of OH minus. Got it? So what do I get here? From here you can see we will get this as 6I2 plus 12 OH minus, and that is giving 10I minus plus 2IO3 minus plus 6H2O. Okay. Now you divide everything by 2. So what do I get? 3I2 plus 6OH minus is giving 5I minus plus IO3 minus plus 3H2O. Right. So this is what you need to finally get. Okay. Clear? Try the same way for the next one. Sulfur giving NaOH, Na2S plus Na2SO3. Try to balance and find out what is the equivalent weight of sulfur. See, I'm pretty sure you must have got up to some point here like this. 3S must be giving 2S2 minus plus SO3 2 minus. And in total, 4 electrons are being transferred. Did you all get to that? Yeah. So, which means I can say that for 3 sulfurs, the total number of electrons transferred are 4. Okay. For 3 sulfurs, the total number of electrons transferred are 4. And for 1 sulfur, how much is the number of electrons transferred? 4 by 3. Correct. So that means what will be the equivalent weight now? Equivalent weight of sulfur will be equal to molecular weight of sulfur divided by 4 by 3. Okay. What if I ask you equivalent weight of S2 minus? What will be the equivalent weight of S2 minus? See, in that case, what you do? You only check how many electrons are being transferred. See the shortcut here. See, check out the total number of electrons transferred. That, so molecular weight divided by total number of electrons transferred divided by the valency factor it has. Sorry, divided by the number of moles it has in a balanced equation. Similarly, if at all I ask you, what is the valency factor of SO3 2 minus? So in that case, how much it will be? Molecular weight by 4 by 1. Okay. So that will be the molecular weight. If I counterbalance this, now you have 3 sulfurs. Okay. It is becoming 2S2 minus plus SO3 minus. So which means we have 3 oxygens. So 3 oxygens here. Okay. And if at all I have to add water molecules here. So where would I add? Because it is in a basic medium, I'll be adding 3 water molecules here and double the number of OH minus. Add them. So what do I get? 3S plus 6 OH minus is giving 2S2 minus plus SO3 2 minus plus 3H2O. Right? So this is how much we need to know. Clear? So remember, in case if you were ever asked what is a valency factor or equivalent weight of the product side, correct? If at all it is about the product side, always check out molecular weight divided by the, uh, molecular weight divided by the number of electrons transferred, that divided by the number of moles that is present or stoichiometric coefficient that are present with that. Okay. So that way you can calculate what is the equivalent weights. I guess all of you understood this point. Right. Okay. So